Hey guys, so today we're going to discuss percent composition. So before we talk about what percent composition is, let's go ahead and take the opportunity to review molar masses for a second. So if I wanted to find the molar mass of H2SO4, which I now know is sulfuric acid, I would go to the periodic table, add up the molar mass for 2 hydrogens, 1 sulfur, 4 oxygens. I would round that to 2 decimal places and I would get 98.08 grams per mole. If yours varies slightly, the second decimal place on periodic tables can vary, so don't worry too much about that. Or if I wanted to calculate the molar mass for calcium phosphate, Ca3, PO4 2, I would add up the mass of 3 calciums, 2 phosphorus, and 8 oxygens, and I would get 310.20 grams per mole. Okay? So that tells me that every mole of sulfuric acid weighs 98.08 grams, and every mole of calcium phosphate weighs 310.20 grams. So now let's talk about percent composition. Before we do that though, let's look at an analogy to think about why we even need to do this. So let's say you have a dog. Okay, so you have one dog. And let's say your dog has a flea problem. So let's say on your dog you have 99 fleas, or it has 99 fleas. So let's say your dog's a Great Dane. It's a very large dog. So now let's say you put your dog in a box or a container or carrying crate of some sort. So inside the box you have one dog, a Great Dane, and you have 99 fleas. And someone asks you, what percentage of the box content is fleas, okay? So I know that's kind of a strange thing somebody asked you, but just humor me here. So if you just based it solely on the number of items in the box, you could say, well, the contents of the box are 1% dog and 99% fleas. Is that a correct statement? Yeah, we could say that just based on counting the items. But the mass of the dog is several, hundred or likely 1,000 times larger than the mass of the fleas. So if we think about this in terms of a chemical compound, we might have H2O. You ask me, well, if you have water, what percentage of water is hydrogen? Well, you might say water consists of 3 atoms. 2 of those are hydrogen. So you could say 66.67% is hydrogen and 33.33% is oxygen. Okay? But kind of like in the case above, the mass of the oxygen, so every oxygen molecule weighs far more than hydrogen molecules. So the mass of the oxygen atom severely outweighs the mass of the hydrogen. Kind of like the mass of the dog severely outweighs the mass of the fleas. So that's why when we talk about the percent composition or the percent makeup of a molecule, we don't talk about it in terms of number of atoms. We talk about it in terms of mass. So if I ask you for the percent composition of sulfuric acid, what I'm really asking you is what percentage of this compound's mass is derived from hydrogen? What percentage of this compound's mass is derived from sulfur? Okay. So a couple of steps to calculating the percent composition. So the first step is to find the molar mass. Abbreviate that MM of the molecule. Okay. Then you want to find the total mass of each atom in the molecule. So what do I mean by total mass of each atom? So let's just say in the water example, there are 2 hydrogens. So the total mass of hydrogen will be 2 times the mass of hydrogen. So I look for the total mass that is derived from that hydrogen there. Okay, so let's go ahead. I'm sorry, I didn't finish the steps. So then you have total mass of atom divided by molar mass times 100 equals the percent of whatever the total mass of the atom was. Okay, so let's look at what that might look like in a few examples. Okay, so the first one I'll ask, or the first one the notes ask, is to find the percent composition of lead 2 chloride. And so I believe the notes went ahead and typed the formula out for you, but you can pretty easily now hopefully go from the name to the formula. So PbCl2. Okay. So the first step in finding the percent composition of this compound is to go ahead and find the molar mass of the compound. Okay. So if I'll go and show you my calculator, what I'm going to do, try to get that glare off. Let's put it down here. Okay, there we go. So chlorine, we have a mass of 35.45. I can just read 2 decimal places off the periodic table, that's fine. I have 2 chlorines times 2. Now look at the mass of lead is 207.2. Okay, so the total molar mass of lead 2 chloride is 278.1. So 278.10 grams per mole. So now I need to figure out what the total mass for each of the constituent atoms is. So the mass of lead here, there's only 1 lead, so it's just the mass from the periodic table, 207.2. Okay. So we'll just call that grams, or we can say grams per mole. The mass of chlorine from the periodic table is 35.45, but I have 2 chlorines here. So the total mass of chlorine, so I can say total chlorine, is equal to 70.90 grams. Okay. So now I can go ahead and plug this in. So I'll set this up. 207.20 divided by 278.10, and I can just say grams over grams so it cancels, times 100 equals a number percent lead. So now I go and set up the other one, 70.90 divided by 278.10 grams times grams, 100, that equals my percent chlorine. Okay, let's go ahead and type this in and see what we get. So 207.2 divided by 278.1 times 100, and you get, so we can round these off to 2 decimal places. So we'll kind of ignore the significant figures rule here, and we'll round percent composition to 2 decimals. That's perfectly fine. So 74.51% lead. Then I go and solve the other one. 70.9 divided by 278.1 times 100, and you get 25.49. Let's go back and check ourselves. This is the percent composition of lead 2 chloride. So if I did this correctly, it should add up to 100. Okay, add it together, it does, I'm good. If it adds up to 100.01 or 99.99, something like that, you're okay. That's within the realm of rounding error. But if you get something that's completely off, you know you've gone wrong somewhere. So let's talk about what this means. So even though every lead 2 chloride molecule has 1 lead and 2 chlorines, 74.51% of the compound's mass comes from lead, whereas only 25.49% comes from chlorine. Okay, so we can't judge the composition of a compound just based on the number of atoms. We have to actually look at the masses to see where the majority of the mass comes from. So let's go ahead and try one more of these. I believe the next one in your notes is barium nitrate. So BaNO3 2. Okay, so add this up in your calculator however it works for you. I'll just show you the process that I use. I typically go ahead and multiply the numbers in my head. So I would do 16 times 3 in my head, then write that in. But let's just go ahead and show what we could do if we weren't going to do that. So let's add up the mass of nitrate. So I have 14.01 plus 16 plus 16 plus 16. Okay, and that's the mass of 1 nitrate, but I have 2 nitrates times 2. Then I add the mass of barium, which is 137.33. So then I get 261.35 as my molar mass. So if your hundredths place differs from mine because your periodic table is slightly different, that's perfectly fine here. So molar mass equals 261.35 grams per mole. Okay. So now let's go ahead and let's just go ahead and set these up as we go. So we'll do barium first. So 5% barium equals the mass of barium, so 137.33 277.33, and I only have one barium here, so I keep that written like that, so I can label that as grams. I have a molar mass of 261.35 grams times 100. Okay, so I can go ahead and type that in. I get 137.33 divided by 261.35 times 100. We'll just stick with rounding to 2 decimals, and you get 52.55%. So I can leave it as that, or I can say percent barium, then my percent nitrogen. Okay. So I want to find the total mass of nitrogen in the molecule. So there are 2 nitrogens here. So the mass of nitrogen is 14.01. Multiply that by 2. You get 28.02. We'll call that grams, divided by 261.35 grams. My units will always cancel here. So type it in, 28.02 divided by 261.35 times 100, and I get 10.72% nitrogen. Okay. So for percent oxygen, if I'm very confident in myself, I can just take 100 minus this number, get my percent oxygen. But then I'll lose the opportunity to go back and check my work by adding them together to make sure they equal 100. So let's go ahead and go through the process and then go back and double check ourselves at the end. So the total mass of oxygen, there are 6 oxygens here. So I do 16 times 6. So I have 96.00 divided by 261.35 grams. So 96 divided by 261.35 times 100, and I get 36.73% oxygen. So let's go back and double check our work now. 36.73 plus 10.72 plus 52.55, and I get 100. Okay, so I know I did the problem correctly there. So if you look, even though there are 6 oxygens and only 1 barium, the compound's mass is still mostly derived from barium there. Okay, so it's important to pay attention to that. And not just say, okay, well, oxygen has to be the most important contributor because there are the most of them. You actually have to go through and calculate the masses out each time. So we'll use these percent compositions to actually find the formulas for unknown compounds coming up in a few videos. So that's the ultimate reason we do this. This is a technique we can use in some chemical spectroscopy that you might do in higher level chemistry, where some kind of instrumental analysis could give you the percent compositions, and then we'll use percent composition to calculate the molecular formula later in the chapter. So one other thing we can do percent composition for, I could ask you for the percent nitrate. And that's probably going to say, what is the percent of nitrate in barium nitrate? So at this point, there's a couple of ways to do that. I could simply add together the nitrogen and oxygen, because nitrate consists of nitrogen and oxygen, and that's obviously the answer. Or I could add up the total mass of nitrate, so the mass of 2 nitrates divided by the molar mass there as well. Okay, so several ways to get that answer, but just be aware, if I do ask you that, nothing changes. So one other thing that we want to discuss are hydrated molecules. Okay, so something like zinc sulfate, and then you'll see times H2O, and there'll be a certain number of oxygens. So let's see in the notes how many you have. 7. Okay. So what this means is that we have a zinc sulfate compound that has combined with water. Okay, so there is water in the ionic structure. So for every zinc sulfate we have, there are 7 waters combined. So this will be a solid, okay, so it's not a solution of water. There is just water in the ionic structure here. Okay, so when we have hydrated compounds, we can ask what is the percent water. Okay, so a lot of times you'll see what is the percent of water in this hydrated compound. Okay, so nothing changes here. The only difference is we consider the molar mass of this entire piece right here. Okay, so 1 zinc sulfate and 7 waters. So go ahead and take a second and try to add up the molar mass of that whole compound there. Okay, so hopefully when you added that up, you got 287.5 0.6 grams per mole, okay? Or 0.60 grams per mole. So if I want to find the percent water, I need to find the total mass of water in this molecule. So there are 7 waters present. So I have 18.02 times 7, and I get 126.14 grams divided by 287.60 grams times 100. So when I do that in my calculator, you get 43.86% water. Okay. So you see that even though this molecule has 7 waters for every 1 zinc sulfate, still the zinc sulfate makes up more than half the mass of this molecule. And because I only ask you for the percent water here, there is no need to actually go through and find the percent zinc, the percent sulfur, the percent oxygen. But we could do that. So let's look at one more example. Let's look at, excuse me, NH4NO3, ammonium nitrate. So I could ask you for the percent composition. I'm going to simplify it though. I simply want to know the percent nitrogen. So I say ammonium nitrate, I want to know what is the percentage of nitrogen in that molecule. So we know the first step is to go ahead and add up the molar mass. So go ahead and try that on your own. So you should get 80.06 grams per mole. Okay. Then we want to add up the total mass of nitrogen in the compound. So be careful here. There are 2 nitrogens here. Okay, so just because they aren't written together, don't forget there's actually 2 of them there. So the total mass of nitrogen is 28.02 grams divided by 80.06 grams. So times 100. Sorry, that G was a little strange. So let's do that. Calculate 28.02 divided by 80.06 times 100. Okay, so you should get 34. I'll write the whole thing out. You get 34.998. So when we round that off, we round that to 35.00% nitrogen. So then I could go ahead and solve for hydrogen and oxygen as well. I just want to show you this example to make sure that you pay attention and get all of the atoms present in the molecule. Okay, so fairly simple. You just have to be sure and keep your numbers straight and be sure you add up the molar mass correctly. So like I said, doing the calculating percent composition isn't always super helpful just on its own. I mean, it gives us some perspective on the actual makeup of a molecule. However, we're going to use this to calculate the empirical and molecular formulas in the next couple of videos, and then we'll do an activity so you can see actually how these calculations are used in forensic chemistry. So these are calculations that are actually very useful in real world situations.